What is going on, guys? Welcome back. In this video today, we're going to take a look at percolation, or in less fancy terms, we're going to simulate processes where things are spreading, like diseases or wildfires in Python. And primarily, we're going to do that to learn skills like animating stuff, simulating stuff, but also the mathematical thing that we're actually doing here, that we're actually taking a look at, is very interesting. So if you like this video, let me know by hitting a like button and subscribing. And now let us get right into it. Alright, so today we're going to do something fun. We're going to simulate processes where something is spreading. And before we build anything, I want to show you the final result up front as a motivation. So I'm just going to run my prepared code here, uv run simulation.py. It might take a while and then it's going to start. But basically, we're going to simulate the process of something spreading. This can be a disease, this can be a wildfire, it can also be something positive. But the idea is we start with a single person being infected or a single tree burning or something like this. Then we have neighbors, and then the whole thing can spread. And the question is, will it span? Will it actually lead to percolation? I think this is the proper term. Correct me if I'm wrong, but basically, will this whole thing spread across the entire lattice, across the entire 2D lattice, or will it stay roughly contained? So will it stop right now here and that's it? Or will it become very big? And the interesting thing is also there is a certain threshold, 59.27%, where if you go beyond this threshold, you're basically statistically an infinite 2D grid, and with enough tries without the randomness being a huge factor, you would basically span the grid, and below that you would not span the grid. And if you add some, if you go outside of the uncertainty window, basically, which I'm doing here by going with 0.83, you're almost guaranteed, or you're very, very likely to spread the entire span and otherwise, or span the entire grid. Otherwise, if you go in the other direction with the same amount, you're basically staying contained. And this is what we're going to build today. This can help you to train your animation skills. So you can also zoom in here, by the way, if you want to see a more detailed view of that. But this is going to be good to learn animation with Matplotlib and also to do something a little bit more mathematical. So that's what we're going to build today. And for that, all you want to do is you want to go to a directory of your choice. In my case, that's going to be the tutorial directory. I'm going to go full screen here. And you can either create a project using UV, you can create a virtual environment, or you can just use your Python installation. The only thing you need is you need Matplotlib and NumPy. So either do pip or pip3 install NumPy and Matplotlib, or if you're not using the core Python installation, you can go with UV init to create a UV project, and then UV add NumPy and Matplotlib. Whatever you do, just get these two packages onto your system and use them. Besides that, we're just going to open up a main py file. In this case, basic one is generated. We're going to empty it so we can start from scratch. And one more thing that I want to do is I want to initialize here, or source activate actually my virtual environment. So I get auto completion, and then we're going to start by importing random. Random is important because we're going to have a 2D grid, and we want to have random people in random positions and also a random starting point. But the spread is not going to be random. All the neighbors are going to be infected. We're not going to keep this complicated. That is basically just a graph. If there is a neighbor, it's going to be an infection there. Then we're also going to say import numpy as np. So that's going to be an import 2. And then import matplotlib.pyplot as PLT for Matplotlib in general. And we also want to have the animation. So from matplotlib.animation import function animation, or func animation. Then what we need to do is we need to define some of the parameters, or some of the conditions that we have here. Now, the larger the grid is, the more accurate this is going to be. So you're going to get statistically more accurate results, or more expected results, if you have a larger grid. But we're going to keep it simple here with 1,000 times 1,000. So if we set this to 1,000, that actually means squared, like this. And then we're also going to say fill percent, or fill percentage. And this is probably the most important parameter here. This is going to be how many of the cells are going to have a person in them. So if we have 1,000 times 1,000, we can say that 40% of them will be filled with people. The other 60% are going to be empty. And we're going to go here with 59.27. And that is the thresholds, this magic threshold that comes up in simulations where basically if you go beyond it statistically, you're starting to span the grid, and below that, you're not spanning the grid. Now, of course, we're going to have some random noise here, so we are going to go outside of the noise window. We're going to try to do that to get the results more clearly, but this is the cutoff value. This is the thing that's somehow special. And the interesting thing is we don't really have a formula for it. So there is no formula that will produce this number that will tell us that this is the threshold to program into a script. It's just a thing that shows up across simulations. So yeah, we're going to start here with 59.27. Then we're going to change this a little bit later. Then also, just for the animation, we're going to have an animation delay. This is in milliseconds. I'm just going to go with 10 here. Feel free to adjust that. If you want to have a slower animation, you have to increase this number, but I think 10 is fine. And now we can start with the entire grid and the entire setup. So we're going to start by calculating the total number of cells. That is obviously going to be size times size. Now you can also say size to the power of 2. I prefer to write size times size because that is more visual. You immediately see size times size, like a square. So I'm going to write it like this. And then we need to say, okay, how many people do we put on this grid? So how many of these cells are going to be populated? And for this, we're going to say that is the total number of cells times the fill percent. But be careful, since we're doing this for the sake of readability here, we have 59% written like this. But of course, the percentage is divided by 100. So if you want to do the calculation, you need to divide by 100. And that is going to get us the number of people that we place on the lattice. However, this number can also not be an integer, so we need to round it to the next integer. So round the result of this calculation. Then we're going to say that the grid is by default just a NumPy array full of zeros. The shape is going to be size and size. The data type is going to be integer. And then we have to determine the positions that are going to be filled with people. So we're going to do this in a flat way. Out of the total cells, we're going to pick num people cells, and then we're going to just set them to a value. So I'm going to say here, positions are going to be equal to NP random choice. Out of total cells, we want to pick num people, and we're going to say replace equals false. Or actually, we need to say size num people, I think. And now these positions are numbers in a flattened dimension or in a flattened way. So we're going to say here grid.flat, and then positions are going to be equal to 1. So 0 is no person, 1 is a healthy person, and 2 is going to be an infected person. Speaking of which, we need to start somewhere. So we need to say that a certain person, a random person, will be infected, and everything goes from there. I'm going to say start is equal to np random dot choice from positions. So one of the people here will be set to 2. Now, to get from this position to the two-dimensional way of writing this, we're going to say here start row, start column. We just use the diffmod function, which will do the division and also give us the remainder. So the remainder of that will return, of course, just the result of the division, and then the remainder, that's the column. Now we basically just say grid start row and start column. That is going to be equal to 2. This is the thing. This is the person that is now infected as the first person. And now then, of course, we need to keep track of everyone who's infected. So we're going to call this our frontier. And that is going to be by default, or in the start, it's going to be the start row, and the start column is a tuple. But we're going to add more stuff as we go on. That is our frontier. Now, for the animation, we're not going to do the calculation while also showing the animation. We're going to do all the calculations first, and then we're going to animate them afterwards. So what we're going to do is we're going to say frames is equal to, and we're going to start with grid.copy. That is the first frame, just a grid with one infection, and the rest will be added as we go. So then we need a loop. We need to keep track of when we have new stuff in the frontier. So when do we have new infections? So while we have something in the frontier, we're going to start with a new frontier, which is empty. And this is how we keep track of the new infections. So basically, new frontier will be empty, and the new infections will be added. If there's nothing, we're going to break out of the loop, because at the end, we're going to set frontier to new frontier. And if nothing was added, basically, we're done. No spreading is going to happen. But before we add stuff to the new frontier, let's work with what we already have. And what we need to do is for every infected person in the frontier, we need to find their neighbors and infect them too if they're not infected. So we're going to say here for row and column in frontier. So for every new infection that we have here, we need to check the neighbors and infect them. So that's going to be a list of neighbors. Neighbors is going to be equal to the following list. It's going to be a tuple, same row and column plus 1. Then it's going to be same row and column minus 1. And then it's going to be row plus 1 and same column, and row minus 1 and same column. So we need to get rid of this here. And now with this, what we do is we say if everything is still in the boundaries, because of course by not checking here we can go out of bounds, which we don't want to. But basically we're going to say for neighbor row and neighbor column in neighbors, so for all of these points, we're going to check if they're in the bounds. If 0 is less than or equal to neighbor row, which is again less than size, and also 0 is less than or equal to neighbor column, and it's less than size. If that is true, then we're going to say, is this position already 2? So if the grid at this position, so neighbor row, neighbor column, if that is equal to 1, we're going to set it equal to 2. Because 0, of course, doesn't make sense. We don't want to infect empty cells. Only if there's a person that's healthy, we're going to infect them. So grid, neighbor row, neighbor column, that's going to be equal to 2. And of course, since we now have a new infection, we need to add this to the frontier. So the new frontier will get this new tuple appended to it. Neighbor row, neighbor column. So in the next iteration, we can look at their neighbors and infect them as well. And once the entire frontier is processed, we can say that the frontier is equal to the new frontier. And if there is a frontier, so if something changed, basically what we need to do is we need to also append to the frames. So frames append frontier. And we also need to check if there is a frontier. So if something changed, what we need to do is we need to say frames.append, and we need to make a copy of the grid so we have something to visualize later. So that is actually the entire logic. So let's briefly recap before we go to the animation. That's already the magic here. We have a grid, a 2D grid, a 2D lattice of size 1000 times 1000. 59.27% of the cells are people. So we have people there, and the rest is basically empty. We start with nothing. We position these people randomly. One person gets infected with state 2, and then what we do is we just go over the infected people. In the beginning it's only 1. We infect all the neighbors. In the next iteration we look at the neighbors, their neighbors, infect them, and the question is, will this span across the entire grid? And to see that, now we're going to code the visualization. I'm going to say figure and axis is equal to plt subplots. Figure size is going to be equal to 7, 7. And then we're going to use the function image show or imshow. So it's going to be image is equal to axis imshow. And we're going to start with frames 0. Interpolation is going to be equal to nearest. Vmin is 0. Vmax is 2. So that's going to show the first frame, and then we're going to animate the remaining frames. Also, since this is an image, let's do axis off. So axis.axis is going to be off. And we also want to have a title. I want to have a title where I keep track of the numbers, not just the visuals. And by default, that's going to show the percentage, or let's call this fill maybe. Fill is going to be the fill percent in percent. Then let's go with the number of people. People is going to be number of people. And then finally, we're going to say infected is going to be 1. And now the only thing that's missing is 2 more ingredients. On the one hand, we need a function for the update of the frames. And then we also need the animation object. So I'm going to say here def update. And that's going to be the frame index as a parameter. And we're just going to say frames equal to frames, frame index to get the respective frame. And to visualize it, we're going to say image set data frame. So that's just going to set the correct pixels. How do we get the infected count? The infected count is basically infected count is going to be just the NP sum of the following. We need all the frame cells that are equal to 2. So I can just say frame is equal to 2. This will return a bunch of zeros and ones. If we sum them up, we're going to get all the ones. So we get all the cells where we have 2, which is the infected state. And then I can copy this axis set title, and we're just going to say infected is infected count. Or actually, I think to do this properly, we need to say title is equal to axis set title, and here we can just say title set title. And then finally, we just return the image and the title, and we create the animation object. Animation is equal to func animation. We pass the figure, we pass the update function, we pass frames is equal to length of frames. Interval is now the animation delay that we defined in the beginning, 10 milliseconds. And then we also say blit is false and repeat is false as well. And then really the absolute last thing we need to do is we need to say PLT show. So if I didn't make any mistakes, that should be the simulation right there. We're going to go and say uv run main.py, and we're going to see what happens actually. Diff mod doesn't work. Expected 2 arguments got 1. Yeah, that doesn't make sense to just pass start here. Yeah, of course, it's start and size. We need to divide start by size. And we have a typo here with title. So just title, not tight. So now we can go and run main.py, and this should now show us the simulation. The calculation takes some time. The longer it takes, the more likely you will see something like a spread. So we're not going to play all of this. We're not going to wait for it to cover the whole thing, because this is the threshold. This is if you have an infinite lattice, if you have a perfect random list with the law of large numbers and everything. We're going to go the safe route. We're going to add something on top of that if we actually want to make it happen, if we actually want to spread it across the entire thing. And we can go below that. So the same amount that we're going to go up, we're going to go below to basically not guarantee, but make it very, very likely that it's not going to spread. And basically, I'm going to abort this now. What we need to do for that is we need to say there is a formula, and I got this from ChatGPT. So if this is wrong, please let me know in the comment section. But basically, there's something called the uncertain zone width. This is basically, you have the threshold, but to really get rid of the random noise, to get outside of the random noise area, you need to add or subtract something. And this number is basically calculated as follows. You take L, which is the size, so I'm going to say size, not L, to the power of -3 divided by 4. So basically, if I open up a Python shell here, that's going to be 1000 and then to the power of -3 divided by 4. So basically 0.0056, but don't forget we're working here with times 100 values, so it's basically 0.5623. So to go the safe route, we're just going to go 57. So that would be plus 0.57 to be super sure that this is going to fill the entire span, or this is going to span, this is going to percolate, I think is the correct word. So we're going to comment this out to not get floating point errors, and we're going to just say, how much is that? That's 59 and then 70 and then 84. That's that. So this should now be high enough to not really guarantee it. You can always have randomness. You can always be unlucky. You can always have a bad starting point. But this should usually lead to a percolation, if that's the correct phrasing. So uv run main.py, and now it should calculate. It should take some time. The more time it takes, the more likely it is to have to do a lot, to infect a lot. So I don't know what the exact formal definition is, but I think that if you go from one side to the other, or from here to here, that's basically spanning the grid, spanning the lattice. So this looks promising, I guess, because it goes off in the different directions. So yeah, you can see that this looks very much like it's spreading across the entire thing, even though we didn't touch the other side yet, and maybe it will fail at some point, it will stop. But you can see that this is a pretty solid outbreak, or a wildfire, or whatever you want to call it. And the interesting thing is, if you just go the same amount down, you will almost never find this. So it's like when you go up, if you go to 60, you're definitely going to find this most of the time. If you go to 58, you're almost never going to find it. And that's super interesting. There you go. Now we touched the right side, so we can actually stop this. I'm not going to keep this playing until the end. But basically, we can now go into our main py file, and we can just do the opposite. So we can go and say Python and say 59.27 minus 0.57. That is 58.7. Now, I would probably go even lower than that to really see the effect, because you will still get very long simulations from that, and I don't want to run all of those. So I'm going to go lower with that value, but let's see, maybe we get a good example right away. Yeah, this was a very quick one, so it's probably not going to take too long to finish. There you go, 508 infected, stop. Now, not everyone is going to look like this. Not every run is going to look like this, but usually it's not going to take a very long time for it to stay contained. It's not going to spread like wildfire, whereas if you go with the other setting that we had, it's usually going to spread like wildfire. There you go, stop like here. Maybe let's do one more time. This was also very quick. Done. Let's try again. At some point, it's probably going to spread a bit more. You still have the chance to go from one side to the other. That's not something that's impossible to happen, but it's just way less likely. Whereas again, if I go back to the previous setting, what was it, 59.84, we're not going to run the whole simulation, but just by seeing how long it takes to start. Okay, this was actually a quick one, so this is probably a bad example. This is not going to go very far. But usually when you run this, you can see it's still calculating, it's still running, which means it's going to do a lot before it stops. It's still calculating, so this is going to be a good span. I'm not going to run this now, but this is going to probably span the entire thing. And okay, this was also a very quick one, but you get the idea. So if you want to go super safe, you would probably go to something like 62. It would still be all around this threshold, so it would be around the 59.27, but you go up a bit, you go down a bit. I think if you go 62.5, almost a run should be a span. Not guaranteed, of course, because you can always end up in a bad position. You can always end up in a local thing that doesn't span well. But usually it's going to be a long run. You can see this takes quite some time to get started, so I can actually already stop. This one also takes a long time to get started. I can already stop. Try it again. Also takes a long time. So these are spanning a very long time. Whereas if I go in and I do something like the opposite extreme, if I go like 50, that would be minus 3. So let's go with 55 or something. If I go with something like this, that's going to always be a very, very quick one. And it's always going to stay contained. It's not going to spread. There you go, like this or like this. Very quick calculations, very quick simulations. It's never really going to spread. This is now a very wide zone that we have here. Like we moved very much away from the actual threshold. But since we're only doing 1,000 times 1,000, this can make sense. And also, of course, feel free to reduce the size here, go with 100. Then we should also do the calculation like this. So we should do 100 to the power of -3 divided by 4. That is now 0.03. Don't forget times 100. So that's actually 3% that we have to go up and down now. So with this, I guess it's fine because we did that basically. Let's see if that actually works. So this stays contained. This stays contained. This stays contained. This stays contained. And now we can go back in and go up the, what was it, 63 or something, 63.5, or was it 62.5? Actually, for the 3.16, that would be 59.27 plus 3.162. Yeah, that's actually a good threshold. These should all spread down. There you go. We spread. Okay, this one actually was contained. This one didn't even get started because it's isolated. But yeah, usually you get a spread from these. That is what we're simulating here. So the goal of this video today, of course, was to show you this mathematical thing. It's very interesting. It's basically a thing that was found in simulations. It's not a formula that gives you that number. It's just the thing that this converges to. So I think it's an interesting mathematical thing, but it's also good as a coding exercise to just play around with this. Feel free to do this maybe in more dimensions, to play around with different parameters, to maybe add some randomness into the spreading if you want to play around with this. But I think that's a good coding exercise. So that's it for this video today. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. Also, in case you're interested, on my website, you will find a services tab and a tutoring tab. There you can contact me if you need help with a project from a freelancer/consultant. If you want to work with me on a project, contact me via email or LinkedIn at the bottom of the pages. Besides that, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching, see you in the next video, and bye.